Hello, everybody, and welcome to this stream by me, one, the only Prepec Tarjan. So, what do we have to do for today's stream? So, let me tell you a little bit about what we sorry, one button. All right. So, what were we doing? So in this series of streams, we're trying to write an L system. An L system being a way to describe a graphical output in terms of grammar. That grammar has some variables, some constants, some axioms, some rules. And then when you start from the axiom and apply the rules recursively over a certain number of iterations, you get a graphic. Of course, we are missing a big piece here, is that each of these symbols, these variables, the constants, needs to correspond to some graphical element. And for L systems, this is done through turtle graphics. Turtle graphics, in case you don't know what it is basically imagine that on your canvas, you have a cursor, which is called a turtle, and then you give commands to the turtle to move on the canvas. So moving forwards or change direction. So move left, move to the right, and continue moving forward. So for example, to write a square, I will move forward, turn to the right 90 degrees, move forward, turn to the right, move forward, turn to the right, move forward, and then we have a square painted using turtle graphics. So once again, L systems work with a turtle graphic system, not the other way around. Turtle systems are here from a long period of time. There is a language called Logo, which was famously used because of that turtle graphic system, a way to teach, especially I would say children, about computer programming. Anyways, last week we implemented the grammar. So basically, we create a rule set and have the ability to add variables, to add constants, add axioms, and add rules. And then when we tell the rule set to have a certain number of iterations, we get the output as text. So the obvious next stream is the next stream. No. The next step is to add that part of the turtle graphics to the system. So the output is not text, it's actually graphics. Now, as for graphics, I'm going to use MacroQuad. So I'm moving to a test project that is all about this MacroQuad library for Rust, which is a graphical library. In my opinion, the advantage of using MacroQuad is that it works natively on Linux. Let me show you. And well, I'm sorry, this is literally the demo, so I didn't choose the colors. Yeah, not very pretty, but as you can see, it works as it says. So this is natively on Linux Wayland. And amazingly enough, it also works on web. Let me see. Yeah. Come on. So, and you can ask me, okay, but Darjin, this is web, and how does this work? Well, the way this works is by having a web page with a canvas, and on that canvas running JavaScript. In this case, is already statically created macro quad JavaScript bundle, and then loading, as you can see, test macro quad WebAssembly. So this is actually our own code, but it is compiled in WebAssembly instead of native, which in my case is Sling, right? So the reason why I chose macro quad is that during development we can make the system work locally, right? The graphics locally, etc. And then at the end, we can compile the application in as a WebAssembly and have it run in a web browser, which I think is quite nice thing to have, right? So that's the reason why I'm using macro quad. But first of all, what we're going to do, you know, how we say, after this long introduction, what we're going to do today. And what we're going to do today is to modify first this test macro quad into actually doing a turtle graphics, at least the minimum set of turtle graphics that we need for our L system. All right, so let me close project. All right, so as you can see, the reason why the background for the test was red is because of this. Typically, L systems are painted on black on white in the background. Is white. As you can see here, there is a macros in macro quad main basic shapes, and the meaning of that is, as you can see, that is going to be the name of the application, at least in the names in the window title. How did I call my project? Darjin. Okay, this company. Interesting. And now you can see we have a white background. So let's start thinking in terms of turtle graphics. So the turtle graphics basically as it basically has a position and then an angle. So when you move forward, it moves forward from that position upward and then draws a line. And then when you turn the angle left or right, and it just rotates to that position so that the next operation about drawing a line goes on a different direction, right? So that's the first thing. What's the second thing? The second thing, let me show you. I think I close, yes, I shouldn't have to, but I close the window. See me? All right, so that's the window. So, so as I was saying, you see the graphics are typical black and white. The next issue that we have with the turtle graphics in this scenario is something like this, right? In this cell system, the move forward has a fixed length. So as you can see, it grows and grows and grows and grows. What's the problem? Given enough iterations, this is going to be completely out of the screen. Then we have a situation like this. In these examples, for the second, fourth, and sixth iterations, actually this is this. It is this. If we try to move forward a fixed amount of space. Basically, the problem with our system is that it can grow very large, and eventually we're going to run out of canvas. So the only solution is basically to create an auto zoom feature, right? What I was thinking, because I don't see any other way to do it, is that our application is going to write the graphics in a two-pass system. In the first pass, it's just going to calculate the bounding box. And in the second, is going to scale the output so that the bounding box of the graphics rests on the screen. That means that the positions and the amount we are going to advance are symbolic, right? We can put whichever number we want there, but the reality is that then we're going to use the auto zooming to calculate the exact coordinates of every point. There are two ways we can do that. The first would be to use floats, right? We can use, let's say, this is just a 1.0. So basically, this point is, well, if this is 0, 0, this would be 0. Yes, this is 2/3 and this is 1/3, which in floating numbers, that's no problem. it could be a problem. However, if we use a second option, which is to use integers. There was a program back in the day, and it's actually mentioned here, if I remember correctly. Yeah, int. So Fractal is or was an application to create graphics. And as you can see, the name comes from fractal and integers, because the first versions only use integer arithmetics for fast renderings on computers in which floating point wasn't a thing. So that's a main point, right? Doing graphics with floating point numbers, that is not something that you realistically want to go to do when doing graphics, or quote unquote game graphics. Obviously, if you're doing scientific visualizations, you may use floating point, but when you need something that evolves, that is quick, etc., using a lot of floating point numbers may not be a good thing, or at least it wasn't a good thing. Nowadays, the coprocessors in the CPU and the GPU can do some wonders in terms of floating point arithmetic. So that's not a big problem. And we are not doing a Mandelbrot set in which we need to do several iterations for each pixel. No, that's not what we're doing. We're doing an L system. L systems typically, as you can see, sorry, I'm moving too fast. Seventh recursion, sixth recursion, eighth recursion, 10th recursion, sixth recursion. We're actually not, in my opinion, not doing a lot of calculations that deserve creating a fixed point system. That could be a thing in the future if we want to do that. I think it could be a good project when we think in terms of Rust and maths. But at the moment, I don't think that we need to do that. So we're going to use floating points. So we're going to have a position. And we're going to have also an angle. As for the angle, we could use numbers, right, between 0 and 360. But here I think that we can directly use the radians, because at the end of the day, then when we do the mathematical functions that we use and we call, sinus, cosinus, etc., we're going to use radians. So the angle is going to be directly in rads. So the next thing that we need to do is, I'm just going to put this, all of these as public at the moment, because I don't care too much about getters and setters here. So we're going to start with an original position. Now that I think of it, you're going to make your typical 3 point. So I need to write a little bit less. So for the turtle canvas, what we need is a turtle, and then we need 2 points. So we're using Cartesian coordinates. So basically the 0 is not going to be at the bottom, it's going to be in the middle. And then we go on the positives here and here. So the bounding box is going to be divided by the minimum, so not divided, described by a pair of positions, this corner and this corner. So the bottom left and the top right. So the idea is that when we, for example, we use the primitive to move forward, and as you can see, we don't put any amount. So this is important. When you write a real turtle graphic system, like the one that Lego had, or move forward and turn the angle, need to specify the angles. But in our systems, this is very fixed. Basically, you move one fixed amount and you turn left or right one fixed amount per application. All right, so basically what we do here is we move forward and we know our current position, which is the position that the turtle is in. So we need to calculate the end position. So obviously here x is self turtle current position x plus, no, this is just mathematics, is self config distance times cosine. This is interesting. I have not taken a look at mathematics. All right, so that would be for the x, and for the y, is y plus distance times c. Okay, so we have calculated the end position, and our current position is this one. So basically, we need to draw. However, as I was saying, we need to have a two phase system, because we have the auto zoom. So we're not going to write. Instead, we're going to first update the bounding box with that end position. So it's going to move the corners so the end point fits in the bounding box. And then we need to remember that we need to add that operation to the list of operations to do. So at the end, when we have done everything, we just say draw it, and then the canvas is going to be printed with everything zoomed accordingly. So that means that in reality, on top of the plane point, we need another structure, which is a segment. With the 2 points, and we're going to have a buffer containing a vector of plane segments. So we just go to the buffer, and we add plane segment, the start being serve current position, and the end being the end position. And finally, okay, 1 second, I want to see the diagnostics. Okay. So I'm going to move this method. Instead of calling it update bounding box, I'm just going to call it update, because that is going to update the bounding box and also change end position to be the new position for the turtle. but let's do it right now. Don't forget. And let me also add some music while I write the code. Basically, I'm going to release times. And finally, now that we have updated the bounding box, we finally change the position. So now we have updated this. So we have our typical moving here, and it makes sense because end position is sent into a new plane segment. One second, because I don't know why it was clearly in our message. All right, and now we have music. I had it muted. Okay, so now we have that there. So basically, that's move forward. Now, if we think of a second primitive that we need, and let me show you. It's in the counter set here. In the counter set, we have draw forward versus move forward. So basically, this is not move forward, it's draw forward. While move forward is basically everything except pushing. In the new position. So we need to create an internal forward action. Which is going to be just drop, but with the catch that we only push if drop is set to true. So now basically draw forward is the forward action, true, and move forward is the forward action, false. Easy. So, why am I getting these errors again and again and again and again? Because it is calling Rust FMC without any addition. But why would it be doing that? That's going to be bother me to knowing. So give me 1 second. And let's try again now with a yeah. Now it's different. It's complaining here about the terminator. Okay. So it is, even though in theory we're using kernel Rust for the formatting, Okay, so let's change this forever and solve this problem. So Rust Analyzer. Now let's take a look at these. Which is strange because it's talking about JSON. What the what? So here it says that Rust Analyzer toml doesn't exist. Okay? But then Rust Analyzer, according to this, doesn't have a toml file. What is happening here? Let's see if this solves the issue. SP client. this pairs with this, and this, this. If you want to change this to this. Let's try last time. And if that doesn't solve the problem, inject this missing outer comment. Okay. But the good thing is that we know that it is already in that file. Okay, and it doesn't restart. So this is very unsettling. Because this that hasn't happened before in other projects where we have in the cargo tunnel file the fact that we're using 2024 edition. Addition. Yeah. Parse, symbols, highlights. Last step check, project and print. Yeah, it works. So I don't know why the Rust analyzer when called like that is not doing its job. Anyways, let's come back to writing code. We think about the error later. Now, it doesn't give me the error. That's the mix. Gives me the error when I save. Interesting. Because it's in the Rust FMT, it's not in the analyzer. Okay, whatever. I'll figure it out. Sorry. So we have a turtle canvas that it is buffering the actual printing of the segments here, and it's keeping track of the correct position here in the turtle. But now we need to implement couple of simple calls, which is turn left, turn right. Let me show you. So we just hit this. Turn left some degrees, turn right some degrees. So if we're using kind of mathematics, and we have the 0 degrees, then when we want to turn left, we are actually going the positive way. And when we're turning right, we're doing the opposite. All right, so two more primitives done. So we have draw forward, we have move forward, we have turn left, and we have turn right. What else do we need? saving the current position values for position and angle in a stack, and then popping from the stack. So that means that on top of the buffer, we need a stack. Now, stacks are implemented using vectors because you can push and you can pop. You see, pop removes the last element. So it works like a stack. And we need to, according to the instructions, we need to reset both the position and the angle. So we need a full turtle in the stack. Now, the important about this is, what about pop? Right, because this is the first time one of these operations can fail, right? Moving left and right and up and down, moving the angles, that cannot fail. Why? Because for positions, they cannot go out of bounds because we are moving the boundaries, literally, and the angles, just spinning around, no problem whatsoever. Pushing, as long as we have memory, we could push. Pops, however, there could be a problem. Right? So what are we going to do about that? Well, what we're going to do in our little system, which again is not a full-blown turtle system, is that when we are compiling the rules, we're going to make sure that the pops operations are matched. So the push operations are matched with their pop operations. Okay, that there is a balance. And that is going to be done at the syntax level. So in that here, we're going to assume the syntax check balanced push and pop. So that when we pop, we cannot grab it directly. We can expect that, right? Okay, so this shouldn't be an issue dynamically. What is happening? We cannot move out of turtle. Okay. And and we cannot do that because it can. And there we have it. So now we have all the operations that we should need in order to draw something. Except obviously the last one. Oh, sorry, we're missing the constructor. So we have start bottom left corner. I'm going to derive default. Or the pinpoint to make sense. Distance, configuring one, is that, is that, remove that for also. Mm. So now when we draw all, work we do is for segment in self buffer. I'm sorry. First of all, we need to find the bounding box. So we have our positions. Endpoints. I'm going to also the partial equality, because what I'm going to do now is if the two corners are the same, basically we're not printing anything, right? This is this is basically empty. So I'm just going to return. So from here onwards, I can assume that we have a valid bounding box. And where do we get here? Screen width, screen height. So first we need to find the width and the height of the box. Which is the top right corner x times the bottom corner x, and the box height is the same for y's. Oh, no, I didn't use it. So with these values and screen width and screen height values, we actually have the zoom factors. Now, what we're going to do is we're going to take the smallest one. The smallest zoom factor between the two. So, because if we got the, no, it's a minimum. Yes, it's the minimum. So everything is inside the screen. So the zoom factor is going to be the minimum between the screen width divided by the box width. Well, there is a problem here. Is that zoom factor can actually be 0, because here we're only taking a look if the to whether the two positions are the same. But let's imagine that we're printing this. Here, the width is 0 because we're just moving upward in a single step. So here the width is going to be 0, and 0 is going to make the zoom factor 0. That's not something that that we want. So we're going to make the smaller the minimum. Let's calculate a zoom default factor, okay, which is just going to be depending on the size of the screen. So basically, what is going to happen is that we're going to take the width, and if the width is 0, we're going to make it 1, and same with the height. So this is actually we're going to take the maximum number between 1 and this, and we're going to do the same for the height. So we guarantee that the max doesn't work, it's not satisfied. Okay. So max doesn't work for floating numbers. That's quite an achievement. I mean, I can see why. It's because floating numbers sometimes have precision issues. All right, so let's do it by hand. Yeah, and now the zoom factor, we have the same issue that we cannot use minimum because this doesn't work with floating points. Why is this using F32 if I'm using F64 for everything? That this doesn't make any sense whatsoever. Because everything is defined. Aha. A screen with F32. That's interesting. Should we change everything to work with F32? I would say that probably they're using F32 because of some fast mathematics they can do. I think that maybe there are some SIMD instruction that packs a position as to F32s inside a 64-bit register. Maybe. So you know what? Just in case, we're going to change everything to F32. Yeah, still in case. So if horizontal zoom is smaller than vertical zoom, then horizontal zoom as vertical zoom. So that was the minimum. And so that's the zoom factor. So now we have the zoom factor. The second thing that we need to find is the zero position, right? Just because, so just, we are not going to be able to draw this because it's going to be centered on the screen, but I prefer that, to be honest. So how do we find our zero position in Canvas? No, let me put this. And now that we have the zoom factor, we need to find the zero position. How do we do that? So the zero position is just the zoomed position. Now we don't need to find the zero position at all, because we're just going to zoom all all the segments here. What we're going to do is going to draw a line. Okay, as you can see is 1, 2, 3, 4 width and color. So we're going to draw a line from a segment dot start dot x Oh, yes, 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 yes. We need to translate them to a position, which is actually is a function of a plane point. Because we need a plane point and a reference. Yeah. So basically, what we need to do is the following: imagine that this is -1, -1, and so this is the corner, and we are at 0, 0. 0, 0 on the screen is going to be this. So if this is -1, -1, this is 0, 0, and this is 1, 1. So 0, 0 is in the center. Why? Because we're taking 0, 0. We are subtracting the bottom left corner, 1, 1, so minus 1. So this is actually becomes relative to this point 1, 1 out of a sum factor that stretches to 2. So basically it's going to be in the middle. Bottom left, which is another point, and a sum factor which is 32. And this gives me another point. So what we take is this minus this. Zoom and see. All right. So So we have now that we have calculated the translations. Now let's unpack the segment. For the start plane point, we're going to translate with regard to the bottom left corner and the zoom factor that we have calculated. We do the same with the endpoint. So now we have both points. And now we would draw the line between start X, start Y, and X and Y. The line for the moment we're going to make it thin and black. Okay, print segment. Segment. Yes. Yeah. Mm. If I can also about this. Mm. Okay, still no problems with the references that quite I mean, in reflecting, I can see the issue is so apparently for is not using iterator, it's using into iterator. So basically taking ownership unless of course use the reference. Makes sense. So this would draw everything. So let's see if that's correct. We are going to create a new canvas in which we're going to do a mapping of 1, and the angle is going to be 90 degrees, turned into radians, which is to be is P divided by 2. Then we're going to draw forward. We're going to draw forward, turn left 4 times. So this should write a square. Now I know what is going to be the problem here. And for the moment, I'm going to hardcode it. So let me tell you what's the problem that I did. The problem is that if I just write a square, and if my canvas sees a square, and I go full zoom, I'm just writing on the edges, and I may not be able to see the output. So if we we go there, when we go there, let's try this one. Well, it draws something, actually. So what about the angle? Pi is this. Pi by 3 should be 60 degrees. So if I start like this, let's say 0, 0 is in the middle, and my angle is 0, so looking at here, I draw forward, move, 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 move. It should have been printing out an hexagon. It did not. So that's concerning. So first of all, we're going to this is interesting. Oh yes, because it is doing it my mistake. Well, anyway, it should be always the same as 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Interesting. So we start at 0, 0, right? And we need to move 1. However, the original angle is 0. So go step by step. We are creating a canvas. Oh, I see the problem. Is that here in forward action, you are calculating the coffee angle and not the turtle angle. Which in this case should change much, but changes some things. And in fact, that was the problem. Now, this is what I'm so this is, yes, let me remove the print lines. So what's the problem? As you can see, the problem is that lines that land directly on the edges are not very visible, right? And that's because the bounding box is exactly to the position of the to the edges of the window, of the canvas. That is because our bottom left corners and top right corners don't have any padding. So how do we add that padding? What I'm thinking is, and that basically works here too, instead of the return, is that once we are going to draw and we know what we want to draw, we're going to extend the bottom left corner and the top right corner by a fixed amount. But that's a problem, right? Because a fixed amount based on so let me show you what's the problem. So this is the image, right? And what we want is that our bounding box is actually this, not all of this. that means that we need to add padding to the left, to the right. So horizontal padding, top and bottom, vertical padding, right? It's nothing new. You can do that. For example, HTML typically allows you to add padding to the majority of the things. You can pad around, but we didn't have any padding at all. Now, the issue with that padding is that we need to change the calculation rules. How? So what I think the easy way to do it is when we're calculating the zoom factor and when we're using the screen width and the screen height, we're going to remove the amount for the padding, meaning the image is going to be slightly shorter. That's the first thing. And secondly, we need to basically do 2 layers of translations, meaning that oh, wait, we actually need to do 2 layers of translations anyway, because a pixel, a 0, pixel is typically here. And the 0 for us is here. So I'm not going to change that out, but you will see that the back is basically, we're going to have everything printed out upside down, if my thinking is correct. But anyway, yes, that's what we're going to do. What we're going to do is we're going to add to our turtle canvas we're going to configure some padding as a breakpoint. Okay, so X and Y, but it's going to apply on both ends, meaning that if I say that there is a X padding of 3, is 3 pixels here and 3 pixels here. So now that we have the padding, how does it go? Well, how it works is that when calculate with the screen width, the pixel width is actually going to be the screen width minus 2 times, remember, because from the is both left and right, the value for the horizontal and the height is going to be screen height. So now when we're trying to calculate the zoom factor here and here, instead of using the screen width, I'm going to use the pixel width and the pixel height. Okay, that's why the zoom is smaller. The issue is if we only do that, oh yes. No, we don't have any padding here for the canvas. And let's say that we're going to have 20 pixels on each side. Sure. Oh, yeah, we must read. Anyways, you see, now what happens is that I have added all the padding here and here. And by the way, why it is padding here? Oh, it's because the window, not the screen. So you see, that's an advantage of what we did is because we're using MacroQuad and basically we're writing all of this frame by frame. When you change the geometry, it changes accordingly. And I think, anyway. The problem, as you can see, is that we have padded to what for the screen is the top left, is the 0 position, sorry, which is what I was saying before, that for us, mathematically speaking, we're using Cartesian coordinates. So 0, 0 should be here if we're talking only positives, but now we're ending here. Actually, the 0, 0 is this, if I remember. The way this is, no, we are turning left, right? We're turning, yes, we're turning left, yes. This is 0, 0. This should be 0, 0, but I think 0, 0 is this one instead. Anyways, the padding is wrong. Why is the padding wrong? It's not centered because we have removed the zoom factor, but here we haven't translated accordingly the positions. So what we're going to do is that this translation is going to get added out. And obviously the end too. And there we have it. Now, the way this is padded, this is not padded to the center, just a minimum padding on the left and on the top. So you can see that when I move here, it doesn't move to the center of the window. That could be a thing. And I think that's what I was thinking about, trying to find out the center point of the screen. But you know what? I think this works for our purposes quite well. So we're going to leave it like that. All right, so as you can see, we have written a very small chartographic application. The problem is that obviously all the commands are done by hand. The next goal would be to integrate these into the L system. However, that has two steps, or it could have two steps. But before I tell you the reason why, I think we are over time to have our daily break, which should be our break, which again is long overdue. So we're going to take it now. Anyways, stretch, right? And walk a little, move a little. Don't forget to hydrate, especially if you are in another hemisphere and it's summertime. And I will see you all in 2 minutes. Good, we're back. So, what was happening with the graphics? We had the graphics working, that's the problem. The issue that was pointing out in terms of integration of the Turtle graphic system with the L system that we created week is the following. As you can see, the L system, for this L system, for this tree, there are these 4 symbols, right? There are 2 variables and 2 constants. In terms of drawing, 0 draws a line segment, so that would be the draw forward. 1 also means draw a line segment, so the difference is the following. If you are creating a real professional system, like let me show you, it's something like this, you can draw this line ending in a leaf. So you can put a leaf, an actual leaf of some sort at the end of that segment, but not here. Basically, this segment ends at the end, this doesn't. One way to think about it is, imagine, let me show you code. Let's say that we make the drawing thicker. You see, the problem is these lines, because they're just square lines, these are going to actually work for the branches, but they are not going to work for the leaves because they're just going to stop on the spot. So we could devise, for example, a scenario in which we create a new primitive called draw a I would say a terminal line, in which at the end of the line, instead of being square, we add a semicircle, so it looks a little bit more natural, right? So that's the idea behind this, but we're not going to implement this. So this has to be mapped to draw forward. This is mapped to draw forward, and this is mapped to 2 operations: push position, turn left, pop position, turn right. So we have an issue with how these L systems are described mathematically and graphically. Mathematically, they're very simple to write, like this. Graphically, now we need to express also how each of these symbols, all the variables, all the constants, are mapped into turtle graphics operations. And we don't have that. So before we say this, so the thing is that the way we created the DL system, right? The ruleset is that the variables are tokens. There's a problem here. This is not the implementation of the other day. Oh, yes. Sorry about that. We did a second implementation, but I didn't push it into Git or anything. My mistake. Yeah, there's the implementation. So the rule set contains a list of tokens, which is good for us because, as we can see here, both variables and constants can be mapped into graphic elements, right? So that's why it's better to call them tokens, because now every token, variable or constant, can be mapped into some sort of graphic set of operations. But here's the thing, we don't have that. For us, a token is just a struct that contains a symbol and an index. So on top of that, we will need to add first of all, a set of graphic operations, and then obviously a way to express that. So before we move onwards, I'm going to clean up this mess. Now, obviously, I need to not modify all the rule sets errors because now the errors are local. Oops, I deleted too much. That's all. And for this one, perfect. So let me quickly push this. Huh. Okay. Okay. So now that I have cleaned up that, as you can see, the issue is that when we are declaring variables or we're declaring constant, we cannot map those um, into chartographic elements. Rather, we need to add those to the rule set at the token level. So a token should become a symbol, an internal index, and a set of graphical directives. And I mean a set because, as we have seen here, the brackets are mapped to two operations: push position and angle, that's the first operation, the push, and turn, right? That's one thing. The second thing is that we need to compute the angles, etc. somewhere. So what are we going to do? I think that the rule set module containing all the definitions makes sense because they're tightly coupled with each other. But while the turtle graphics is kind of tight, I think I am going to put that into a different file. So I'm going to create a new file that is going to be called turtle system. Turtle map. Turtle map is it is to map turtle graphics elements to and system topics. And that means we need to add these two. So basically what we need is an enumeration which we are going to call turtle action, which is going to be basically the 6 that we have defined in graphically, right? It's going to be roll forward, move forward, turn left, turn right, push, and pop. So the idea about that is to add into our tokens a vector of turtle actions. That way, when we at the end we call the iterate, the iterate, instead of giving us the list of final token, iterate give us the list of operations, okay, as a vector of turtle elements. Why? Because then basically iterate, we make it return that vector of turtle elements. And then in our main application, which is the one that we have working with before in the stream, would create internally panel system. It will pass along all the rules. It will call iterate. It will get the vector of the operations, and then it will just map each of these enumerations into one of the operations that it can do in the turtle canvas. Now, the reason why I am doing it this way with turtle actions that are not directly calls to the graphic systems, basically to loosen the coupling between the L system and the graphical system. So one is going to pass along a list of turtle actions, the other is going to take the turtle actions and call the corresponding method with a match, right? So that's basically that. That's one thing. The second thing is obviously the same way that we're adding a variable, right? Imagine that in here, I say add a variable, and the variable is a symbol, and also the list of operations, right? Imagine that I modify this. So it receives a vector of operations, right? So I can do turtle elements push to element and start an action. Push said that it was turn left. Turn left. Right, something like this. What's the issue? The issue is here. We are doing a push in one element. We're doing a pop in a different element. So when we're adding a variable, we cannot check if the pushes and the pops are balanced with each other, which is a prerequisite that we have established in the graphical part. So this is something that during the final set of the check, here in log, we will need to check. So why did I create this as a different thing? I was going to add more things here. That's for sure. And maybe I will in the future, so I'm going to keep this again separated from the ruleset. So as I was saying, now we're going to define the token to have a a graphic representation, which can it be a slice? Not because it doesn't own the slice, it could be a box instead of a vector. Okay, so here, because so there are some instances here in which I could have used a box of a slice instead of a vector, thinking, for example, the axiom, most likely. Let me check. When we're setting the axiom, we're setting a representation here, and we're just calculating an error chase parse. And the error chase parse give us a result in a vector. But here's the thing, it gives us the representation as a vector for right-hand side rules that they're not going to change. We need to think about that, but not now, right? We're going to pin that idea that maybe some of these things, like for example, tokens, no, because they grow all the time. Rules, they grow all the time. However, a rule is only declared one. So this shouldn't be a vector, but instead a boxed slice. So it cannot grow later. I think that makes more sense. But we're going to do the correct thing here to start with the graphics. So we are creating a token. We need to provide a box of turtle action of a slice. However, there may be some elements, let's see, that don't have a graphical output. So does here video do here you see X does not correspond to any drawing action, meaning that there will be some times in which we don't have anything. So in theory, a box can hold an empty slice, which is simpler than having a sum of a box of a slice. I think that makes sense, so we're going to keep it like that. Anyway, so now we have and now we have these as tokens. This is going to give us some errors. Right, because it should give us some errors. Why am I not finding syntax errors here? Oh, yeah. Cool. No, trade clone is not implemented. Fractal action. So that yes. Now in the initializer of token in line 86. Yeah, sneaky. So obviously here we need to be provided the graphics as an slice of interactions. So the graphics is le pasaron directly the box. Right, so we have now solved the problem at this level, and we have the problem in the colors to add token, which are add variable and add constant. Why? Because in both cases, we need to be provided with further actions. In graphics into box or boxed. So to back into looks like it works. I thought it would. And all the problem is that in our set, in our usage, okay, and now I'm going to make an error just because I can. No. Yes, the field graphic is never read. That's absolutely correct. And token has a direct implementation for the trade clone. Interesting. You're here. Oh, yes, I understand that. Graphic is not used even if it's used by the implied clone. Okay, I understand. Yes, this not used. Why this not used? Because now we need to modify the locking mechanism. How so? So the issue is that we cannot fully enforce the fact that an air system has a balanced push pop, right? Uh, what it is happening is that here at the singular rule level, in this case, do we have a different system in which the pushes and the pops are not the same rules? No. So basically, in the L systems that we're using so far, the push and the pop operations are always balanced inside the same rule. And for the moment, I think that's a good idea to check it out at that level because it's kind of easy to do. So we're going to keep that in mind, meaning that when we're adding a rule, a rule, the rule can only be declared if the token has been declared. No, I see the problem. The problem is that it doesn't take into account, if we do it at the rule level, it doesn't take into the account the axiom. So it should be here at the RHS parse. In which it is pushing the different symbols. That balance need to be happening. So first of all, we're going to create a new error type that is going to be unbalance the stack. So if we do more pushes than pops or the other way around, we get this error. We can actually find out the problem here at this level. How? We're going to create an internal variable, which is going to be called the stack level. Which is going to be a signed integer. No, sorry, integer. So when we find a symbol, you see we can find the token. well, which is actually the token index, right? But now if we go to the actual tokens, right? The tokens were actual tokens and they contain the graphics. So, and I'm going to call it stack delta. Well, in fact, you can implement it here. Implement action. I think stack delta of slice of total actions. What happens is we start from 0, and then for action in this slice. For every action, we are going to reach the action. In case the action is a turtle action push, we're going to get the level increased 1. In case of pop, we reduce 1. And for the others, we don't do anything at all. And we return that. Let's see this. So now when we are parsing this, we get the token. Why this not? No, it doesn't complete. Yeah. Now, the graphics is a box. So I think we can use it directly. right? And if this is not zero, right, we don't have a balanced system of push and pop in a single right-hand side, so either a rule or the right-hand side of a rule or the axiom, then unbalance the stack. What's happening? What is happening? Okay. There. All right. So now, when we're setting up the rules, we go token by token. So what's happening? So the axiom contains A, and A has a single push. That's going to break directly. Oh, that's a good catch. If I add a new error, I need to know how to print that new error. Rule as balanced push pop. There's and balance the stack. Very well. So first of all, we're going to change this rule set to a rule set that uses the pushes and pops. So not the Cantor set, which is the example that I have used so far. And now I don't find the push. Here, that tree. So we're going to implement this fractal binary tree. So we have an empty rule set. We have a variable called 0, a variable 1. 0 draws a line segment. So forward 1, 2. Then we have two constants. First is the open bracket. And it has two actions. One is the push. And the second is turn left. And then we add the second constant, which is the closing bracket, which is the pop. And after it. The axiom is 0. And the rules are 1, becomes 1, 1, 0 becomes 1, something like that. We're going to iterate only 2 because this can grow very quickly. Unbalance the stack. Now we have a problem because the stack is balanced. I see the problem. So this is the balance for a list of actions in a single symbol. In a single symbol, it is unbalanced. Instead, what we need to do is to modify the stack level with regards to that symbol. And only at the end of the parsing, mm, let me do it wrong. Mismatch it, types expected. I 8. I 8. See. Okay. Perfect. So yes, 1, 2, close 2, close 1, 1, close 1. One, 1, 0, 0, 1, 0, 0. Perfect. It matches. So that's all right. So what's the last thing? The last thing is what I was saying before, is that iteration doesn't return bool, but actually returns a sequence of turtle actions. Now, because it is returning, it needs to put it in a box, right? It could put it in a vector so it can grow, but I think that it can build it that way. So if it is log, it's going to return box. New. Okay. Both and come on. It's a box of turtle action. This works all the time. Yeah, it's a box info sequence. Okay. Now what's the problem? Locus of a reference of a device. So now this is not an error. Hmm. Just into box. That's my question. Hmm. Okay. All right, so let's do it like that. So I think it is better if we do it that way, in the sense that right, so that side is correct. Or you have been very silly because you can just create it anyways, a vector. And if it is locked, we return sock into. It also works. Yes, but empty box is going to be useful anyway. So, once we have everything at the end, instead of printing out the output, it, well, so the same way that we have RHs as a string, RHs as a string, we are going to do RHs and right. We're going to basically copy this formula, which we're going to iterate for all the indexes in the right hand side, we are going to get the map. Get the graphics, collect. I don't think this works directly. Type annotations needed cannot infer type of the type parameter be declared on the method collect. Consider specifying the generic argument vec. Absolutely. Oh, from box starter action. Mhm. Yep. Yeah, this iterator is not going to work. So append only works with another vector. Push is one element. Append is not going to work. Yeah. So this push adds a single element, and appends a vector. Extend. Clones and append all the elements in the slice to the vector. Expected a box. If I do this, expected found. Okay, and now we convert. But I thought into box slice. That's the method that I was missing. Okay, here I cannot use it here. Okay, we're good to go. So now we have an RHS starter. So here, finally, Welcome back. So let me 1 second because I have just seen that the stream was cut down and I can see that the bit rate is unstable. So 1 second while I see for how long has this been out. So 2:59:55. So almost 3 hours. So I don't think you have missed much. So I'm sorry because I don't start the streaming and the recording exactly at the same time. Okay, so if the recording is 3 hours, 5, that typically means an stream of around 3:10. So you have been missing the last like 10 minutes, I think. I'm sorry, sometimes I focus on the documentation and the code and I cannot see the chat or the state of the um, stream. I need to find out a way to solve that. So basically, what have we done in the last 10-15 minutes? So we had the rule set changed to one that creates a fractal tree, and we have the iteration works, and we have also added syntax checks to see that the push and pop operations on the stack are balancing each other. And then what I want to do is to change the iterate function so it returns the full list of turtle actions to be done. So basically our graphical application, the one that we work with at the start of the stream, today's stream, and what was it? It can read that list and actually draw things on the screen, right? That's the point. And so in order to do that, we have this box of turtle action, of a slice of turtle action, and we have created this method, edge as turtle. Just go into each of the tokens as indexes in whatever it is passed along, and is going to add the graphics. Is going to collect the graphics into a vector, and that result at the end goes into a box slice. So what I was going to do now is to get that. Two, 6, 7. And close the limiter. Yeah. So what I want to do is to print the graphics. I don't see it. Oh, in this delimiter, pretty close. No, turtle action doesn't implement debug. No, it does. Well, actually, I saw something. I saw something very, very cool the other day is defining debug only for non-optimized builds. And I need to find that code and apply it here because obviously we don't want this to be printed out just in a while. So draw forward, push, turn left, draw forward, push. Turn left, draw forward, pop to right, draw forward, pop to right, draw forward. Push to left, draw forward, pop to right, draw forward. Right, so in theory, if our application follow these rules, it will print out the tree. Meaning that the only thing that we need to do is to basically transpose this rule set and this turtle map libraries for the other application, and the other application it would just excuse me. There we have it. So what we need to do is in the other application, just use this, and then instead of printing the turtle actions, actually doing the actions, right? And I think it is easier the other way around. So taking the code, test of what all right, the implementation of the turtle canvas. So having basically all of having the turtle canvas as a library, and then in a main that obviously will change calling the turtle canvas based on the result of the turtle actions. But that's going to be for tomorrow. For today, yes, it was kind of a pity that the stream got cut almost at the end. Right, so today we have something really nice happening. I think that maybe off stream I'm going to take a look at some of those vectors and make them into boxes as we did with the graphics. I don't think that saves a lot of memory, but it has an implication because when it is boxed, it cannot grow. So it eliminates a potential bug in which someone tries to fiddle with the roles or the tokens after the fact. So I will do that off stream, and then tomorrow we're going to basically integrate the code that we did at the beginning of the stream today with the turtle canvas, integrated into the main. So we actually print in this case, the little tree. All right, so this has been, again, except for the disconnection, this has been a very interesting stream. This is basically my first stream drawing things on the screen. I'm more like a backend developer. I think that it shows in my channel art and the choice of colors today. But in any case, I hope that inspires you to make your own implementations or artsy implementations. We're going to continue tomorrow with the integration, and then we will do other things like getting the rule set be specified via a string. So there's a single entry point with a method that receives a string and can build everything and print everything, so that ultimately that function can be compiled into WebAssembly, be called into JavaScript. So we have basically we can imagine we load the script, and we call instead of the main, we call a method from JavaScript, and that method has as parameter a string, which gets then printed out. That way we can foresee in the future adding a user interface to the web page, so we can actually put the L system there in a text box and click a button to draw and everything gets drawn there, right? That would be nice. But yes, for tomorrow, just step by step, we're going to make the drawing work. So other than that, thank you very much for choosing to be here with me in the stream, or thank you very much for watching the VODs, either here on Twitch or on YouTube. This has been the Perfect Argent signing off.